we're going to look at another example of comparison test of infinite series. And the example we'll be looking at is we want to determine if the following series converges or diverges, and that is the series starting at 5, n equals 5 to infinity, of 3n divided by 5n minus 9 raised to the nth power. Notice the series starts at 5 and not at 1, but as you know, when it comes to convergence or divergence, it doesn't really matter. We can rearrange any finite number of terms in the series, and that will not affect convergence or divergence. So here I'm going to record or write the comparison test. There are two parts to it, but this is the part we're going to need. So suppose that we have two series, and they start at some number n sub naught, which could be 1, which could be 100. So this just represents the starting point of a series, could be anything. And the series are a sub n series and b sub n series, and we require that there be, both of them are positive term series. So an is positive, b sub n is positive for all n greater or equal to n sub naught. And the part we will need is if the b sub n series converges and the a sub n's are smaller or equal to b sub n's for all n, for n greater or equal to n sub naught, then the a sub n series must also converge or will also converge. Okay, and so let's I also, before we go ahead and solve this problem, do this example, let's review briefly a geometric series. So geometric series again could start with any number. So we'll write this as the summation from n equals n sub naught to infinity, and here's what it looks like: some constant a times r to the n. R is called the common ratio, and this series will converge as long as absolute value of r is strictly less than 1. That means that r must be greater than -1 and less than 1. And the geometric series will diverge if absolute value of r is greater than or equal to 1, which means that r itself is less than or equal to -1, or r is greater than or equal to 1. And now let's return and determine if the series starting at 5 to infinity, 3n divided by 5n minus 9 to the n converges or diverges. So first we notice that 9, just a pretty simple fact, and this will be our starting point, is 9 is less than or equal to n if n is greater than or equal to 9. So greater or equal to 9 could be 9, 10, 11. If we multiply both sides of this inequality by -1, we get -9 is greater than or equal to -n. And if we add 5n to both sides, the inequality doesn't change. 5n minus 9 is greater than or equal to 5n minus n, which is 4n. Now if we flip them, 1 over 5n minus 9 is less than or equal to 1 over 4n. And this is for n greater than or equal to 9. I know our series starts at 5, but it really doesn't matter. And now we put 3n in the numerator of both parts of the inequality. So 3n over 5n minus 9 is less than or equal to 3n over 4n. And look at that. 3n over 4n is 3/4. So we established that for n greater or equal to 9. And now let's raise both sides to the power n. That will not affect the inequality. So 3n over 5n minus 9 to the nth power is less than or equal to 3/4 to the nth power. And now let's call 3n over 5n minus 9 to the n. Let's call that our a sub n sequence, and 3/4 to the power n b sub n. And this inequality is true for n greater or equal to 9. As I said, the fact we start at 5 is really irrelevant when it comes to convergence or divergence. So the series 9 to infinity of b sub n, which is the summation from 9 to infinity, 3/4 to the power n. We know that this is a geometric series, and this series converges because your common ratio r is equal to 3 over 4, which is of course between -1 and 1, or absolute value of r is strictly less than 1, and that determines the convergence of this series. And so now the a sub n series starting at 9 is squeezed in between 0 and the convergent series b sub n. So 0 is less than, the series n equals 9 to infinity is greater than 0, and that's of 3n over 5n minus 9 to the power n, and that in turn the series is less than the summation from 9 to infinity of 3/4 to the n, which we know converges. And now by comparison test, we know that the series in the middle of this inequality, the one we were looking at, namely the summation from 9 to infinity of 3n over 5n minus 9 to the power n, converges. That's the a sub n series. It converges by the comparison test. And now we look at the original series the original series started at 5. All it does is we add the n equals 5, 6, 7, and 8 term, which are finite numbers, to a converging series, and that series remains convergent. So we can now conclude that the series 3n over 5n minus 9 to the n, starting at 5, that's the one example originally had, also converges. And the reason for that is we just add, we have a converging series starting at 9, and we add the 5, 6, 7, and 8 term, 4 more numbers that are all finite to already a finite number, and it remains finite and it remains convergent.